All right, chapter 9, problem 13. In this problem, we have the same bridge, except that now the cables are under tension, and right in the middle of the bridge, there is a car. All right, it's a 900 kilogram car that's halfway between the hinges and the cable attachment down here, right? And the bridge is supported by the hinge and the cable only. All right, so we're going to find the force on the cables. All right, find the force on the cables. Well, one thing we can look at right now is we can break the force onto the cables down into T sine theta, which is its vertical component, right? And T cosine theta, which is its horizontal component. And the force here, right? The force has an F sine theta. Well, this is 40 degrees on T. Let's not get theta and 40 degrees confused. Just saying theta out of habit. And F cosine theta component, right? And we don't know theta. But we do know that over here it's 40 degrees. Okay, so let's write down the torques, right? What are the torques we have? Well, again, we're going to use the hinge as a pivot point because that means we don't have to worry about what the force on the hinge is just yet. And so the torque due to the weight of the bridge, that's a negative torque minus mg times times 1.5 meters. The torque due to the car, again, remember the car is in the middle of the bridge, is also a negative torque. That's 900 kilograms times 9.8 meters per second squared times 4.5 meters. It's a 9-meter bridge, so halfway point is 4.5. Right? All right, and then the only positive torque we have is due to the tension, and it's just the vertical component. All right, T times sine of 40 degrees see if I can get this right, plus T times sine 40 degrees times 9 meters. All of that adds up to 0, right? Okay. mg, let's get mg real quick. That's 2,500 kilos times 9.8, right? 24.5. And then let's get the torque times the torque due to the weight of the bridge. 1.5, so 36,750. The weight of the car, 900 times 9.8, and the torque due to the car. All right, and let's get sine of degrees, nope, radians of 40 degrees, and that times 9. All right, so if we solve for t, we've got t equals, and so there's the first term, 36,750, right? 36,750 Newton meters, plus, then there's a second term, which is 39,690 Newton meters, all divided by the 9 meters times sine of 40 degrees, which is 5.79 or 5.785. All right? So what is the tension? Sum those two torques divided by that. Okay, 13,213 or 13,200, 13,200 newtons. That's the tension in the wire. So find the force on the cables. we've got it, 13,200 newtons. Okay, that's it for part A. And all we need was the torque equation, right? Part B, find the direction of magnitude of the force exerted by the hinges on the bridge. Okay, so now we got a couple of different equations to set up. One is, what is the sum of the forces in x, in the horizontal direction? Well, it's got to be 0, but those are F times cosine theta, right? Minus T times cosine of 40 degrees equals 0, right? Okay, so that gives us F cosine theta equals 13,200 newtons times the cosine of 40 degrees equals 13,200 times, let me just put that in, equals 13,200 times the cosine of radians of 40 degrees is 10,100 newtons, right? Okay, so that's from horizontal forces. Now let's look at vertical forces. F sine theta is the vertical force at the hinge, right? Minus mg, the weight of the bridge, minus this 900 kilograms times 9.8 meters per second squared, which is the weight of the car, plus t sine 40 degrees. All adds up, oh, pardon me, all adds up to 0. Okay, so if we solve for F sine theta is, okay, the weight of the bridge, weight of the car, right? I should actually remember 24.5, 88.20. So 24,500 newtons plus 88.20 newtons minus T sine 40 was that's T cosine, okay, equals the tension times the sine, radians of 40 degrees. T sine 40 is 8485. 485 newtons equals, okay, so now 8485, we want F sine theta equals that plus that minus that, right? 24,835. 24, F sine theta is 24,835 newtons. All right, so we now got sine theta and cosine theta. F sine theta and F cosine theta. So here's what we're going to do. We're going to take F sine theta, right? We're going to divide that whole thing by F cosine theta. So what does that equal? F sine theta divided by F cosine theta is, F sine theta is 24,835 newtons, and F cosine theta is 10,100 newtons, right? Okay, so if you notice F sine theta over F cosine theta, the the f's cancel out, and we're left with sine theta divided by cosine theta, right? Divided by cosine theta. Now sine divided by cosine is just a tangent, right? So tangent theta equals what's 24,835 divided by 1010. 24,835 divided by 10, 2.4589. So 2.4589, right? All right, and so that means theta equals the inverse tangent of 2.4589 equals, okay, let's take the atangent of that, and now we have to convert it to degrees because Excel, so 67.9 degrees. Right? All right, that tells us, right, that this angle right here, that angle is 67.9 degrees. Okay? All right. Now that we know that, how do we get to the force? Well, we go back and we pick up one of the other equations, one of the equations we already have here, like F sine theta or F cosine theta is 10,100 newtons, right? So let's go with F cosine, F times the cosine of 67.9 degrees, right, equals 10,100 newtons. Well, F then is 10,100 newtons divided by cosine 67.9 degrees. Okay, so what is the magnitude of F? Equals 1000 divided by cosine of radians of 26,810. 26,810 newtons. That's the amount of force on the hinge, and it is at an angle of 67.9 degrees above the horizontal. Okay, that's part A and part B of problem 13, and we're done.